Hello all. Today, I'd like to talk to you about acid, character, and pH. Here, we're going to examine first off different factors that affect the strength of an acid. Not just saying that an acid is strong or weak, but what goes into determining exactly how strong an acid is on a continuum. Next, we're going to take a look at pH, the definition of pH, and how it's related to acid strength and character. And then finally, we're going to take a look at hydrolysis reactions, where we see things acting as acids and bases, even though we initially might not predict that they're an acid or a base, and this has to do with conjugates of acids and bases. Well, to start off with acid strength and acid character, the first thing to talk about is just that we know that acids, besides strong acids, exist in some sort of equilibrium reaction. That is, that if we have some acid, HA, then it exists in an equilibrium between H plus and A minus, where A minus is the conjugate base of our acid, and H plus is the ion that in solution actually gives it its acidic properties. Now, in this example here, we know that since it's an equilibrium, there's going to be some type of equilibrium constant. And what we give the name of this constant is Ka. It's the acid dissociation constant. And we could write an equilibrium expression for our Ka. We could say that Ka is equal to H plus times the concentration of A minus divided by the concentration of our acid, HA, because we know that our HA is always going to be soluble in our water. At least we're going to assume that it is. Now, I'd like to take a look at three examples of different acids and their different Kas. So the first one we're going to look at is HOBr, and if you measure its Ka, you're going to find it to be 2.5 times 10 to the minus ninth. Then we have HOCl, hypochlorous acid, which we've already seen before. That's the acid, that's the analog of hypochlorite, which is in bleach, and that's Ka. Looks like it is 2.9 times 10 to the minus 8th. And then finally, we're going to look at hypoiodous acid, OI, and it has a Ka of 2.3 times 10 to the minus 11th. So the first way that we can measure the strength of an acid is by analyzing their acid dissociation constants, because we know that weak acids exist in this equilibrium relationship, and a strong acid goes to completion. Well, remember that completion just means that this arrow, this equilibrium arrow, lies completely to the right. So the Ka is really, really, really large. It's really, really larger than 1. In fact, for many acids, we sort of describe their Ka as being near infinity or extremely, extremely large. So similarly, for weak acids, the larger their Ka, the more this looks like a completion, and so the more that they seem like a strong acid. Now, none of these acids are strong, but they're going to be stronger than other acids. So let's take a look at these three here. HOBr has a Ka that's 10 to the minus ninth, HOCl 10 to the minus 8th, and HOI 10 to the minus 11th. And so because HOCl has a Ka 10 to the minus 8th, it's the biggest one. This acid here, if we evaluated these in terms of strength, our HOCl is going to be number 1 in terms of strength. It's going to be stronger than either HOBr or HOCl. Now, the other two to compare them, we have 10 to the minus 9th, 10 to the minus 11th. We can clearly see then that number 2 is going to be our HOBr, and number 3 is going to be our HOI. And it's simply comparing the relative equilibrium constants of these acid dissociations. Now, if you think about it, remember, we had said that this, H+, that's what provides our acid character in solution, right? H+ is what makes an acid an acid. That's why all of our definitions somehow involve the proton or H pluses in solution. Well, if the equilibrium constant is larger, this reaction lies further to the right, there's going to be more H plus in solution, and thus it's going to act more as a strong acid. Now again, we're not talking about these acids as being strong, but just that they are stronger weak acids. So one way we can determine the strength of an acid is just looking at its acid equilibrium constant. Now, there are other factors that influence the strength of acids, and we're going to take a look at 3 of those factors today. The first one has to do with the electronegativity of the anion, or what other thing is attached to our H. So the acids we're going to look at here are going to be, or acids I say, we're going to look at 4 compounds and evaluate whether they're acids or not, are CH4, NH3, H2O, and HF. So you'll notice that all of these have an H attached to them, and all of them are in the second row of the periodic table. They're in the second period. And so as we go across a period, so across a period here, I want us to think about what happens to the electronegativity of our anion here. Well, as you go from carbon to nitrogen to oxygen to F, you have an increasing electronegativity. And so that means that between H and that thing, we have an increasing END, electronegativity difference. And as that electronegativity difference increases, we get more ionic character. That is, that bond begins to be more ionic than it is covalent. A CH4 bond is barely polar at all, whereas an HF bond is extremely polar. It has a lot of what we call ionic character. And so the more that this bond begins to look like an ionic bond, the more easily it's going to ionize in solution. And like we had seen back here, the more that this acid ionizes, the higher the Ka, the stronger that acid strength. And so as we go across a period, we have increasing En, increasing ionic character. That means we have increasing acidity. So as you go across a row, you have increasing acidity. And this just makes sense. We know that HF is an acid, a weak acid, but still an acid. Water, however, we don't think of water as an acid, and NH3 we think of as a base. So as we go to the right, you get base, not really a base or an acid. Oh, now we have an acid, we're getting increased acidic character. Now let's start thinking about down a group here. And the way we're going to do that is we're going to start thinking about bond strength in this example here. We're going to think about bond strength. So to think about bond strength here, let's consider HF, HCl, HBr, and HI. Now you already know that 3 of these are strong acids, namely the 3 below HF, and one of them is a weak acid, HF. So we already can kind of see the trend that's going to be here, that we have increasing acidic character down a period. But we want to think about why we have increasing acidic character. Well, as we go down a period, what happens to the size of these anions? As you go down a period, we have increasing size of the anion. And as you have increasing size of the anion, the bond that this forms, as we know, bond strength is inversely related to size. A really short bond is much stronger than a really larger bond. And so as we have increasing size of the anion, we have decreasing bond strength. That decreasing bond strength then is a huge factor. As you decrease the bond strength between the H and the F, or the H and the Cl, suddenly it becomes easier for that H to pop off. And we know that acids love to have that H pop off and form an H plus ion. So decreasing bond strength leads to increasing acidity. So to sum up what we've seen so far, as you go across a period, as you go from left to right on the periodic table, we have increasing acid character. And as we go down a group, we have increasing acid character as well. Now, both of these 2 examples have dealt with what we call binary acids, which just means we have H and one other element. But we're going to go ahead and take a look now at one more factor, and that is to deal with acids that have another element in them, and that element is oxygen. So if we take a look at elements or acids that contain oxygen, typically we want to be taking a look at the HO bond. And let's actually return back to those first acids we looked at today that included different X's. And I'm going to say X is either Cl, Br, or I. looking at the acid dissociation constants, we saw that HOCl was a stronger acid than HOBr, which was a stronger acid than HOI. We want to think about why that is. Well, again, just like we saw in example 2, to be a strong acid, the weaker this bond, a weaker OH bond equals a stronger acid. And so anything that's going to weaken this HO bond is going to increase the strength of the acid. And the way to weaken this bond is to have X be a very electronegative element. So the greater electronegativity of that element that we have here, X, the greater its electronegativity, the more electrons it pulls toward it. That means the greater acid character. Character. Okay, and so what you're going to see here then is that as we go from I to Br to Cl, you have increasing electronegativity, thus this bond becomes stronger. This bond then becomes weaker because those electrons get pulled over to that very electronegative element. That makes these a stronger acid. So that explains this trend that we saw from the Ka data. Now, this is important. You'll notice then that the acids actually acidity went up as we went up the group, which is exactly the opposite of what we saw before. That's because before we were dealing with just binary acids, HF, HCl, HBr. Now we're seeing acids with oxygen, and it reverses the trend. That with this oxygen here, we see that as we go to more electronegative elements, we then have a stronger acid. The other factor that influences oxygens is just that the more oxygens we have, you have more acidity. Because more HO bonds to be interfered with, the greater that acidity is going to be. So the more oxygens, the more acidity. And there's no better example of this than taking a look at the chlorate series, for example. If you take a look at HOCl, that's a weaker acid than if you have, and I'm just going to write this a different way, HClO, if you look at HClO2, which this is hypochlorous acid, this is just chlorous acid. Then we're going to take a look at chloric acid, HClO3, and then finally the one acid we know that's strong in this series, which is HClO4, which is perchloric acid. It's one of the strongest acids that we know of. So noting that more oxygens gives you more acidic character is important as well. So to kind of review, we've seen that as we go across a period, we have increasing electronegativity. That leads to increasing acidic character. As we go down a group, we also have increasing acidic character due to lower bonds. And so we can summarize that using a chart that you'll see in your text, that if you look at the binary acids, you get increasing strength across a group and across a period, and increasing strength down a group. That's been acid-base character so far, but now let's go take a look at a way that we can actually measure the acidity of something and get into some quantitative details here. So the way that we take a look at this is using the concept of pH. Now, the pH scale you might be familiar with so far, but let's take a look at how they developed it first. So the first thing we're going to take a look at actually is just water. If you have water, we often say that pure water doesn't conduct electricity, but that's a little bit of a misnomer. Pure water doesn't conduct very much electricity. There actually are some ions in water, and we can figure out why. The way that happens is due to what's called the autoionization of water. Auto, meaning self. So water can actually ionize with itself, and we can take a look at why. If you take two water molecules together, we've seen before that water can react with both an acid and a base. That seems to kind of imply then that if we take two waters together, one of these waters could react with the other one to donate a proton. This one would accept a proton, forming an H3O plus and an OH minus. In this way, water is acting as both an acid and a base. We call that, when something can act as both an acid or as a base, amphoterism, or that it is amphoteric. So amphoterism acts as an acid and a base. So there are very few compounds that can do this, but there are some that can, and one of the most important ones is water. So here we see water acting as both an acid and a base. Now, as it does this, we can see that it's going to form two ions in solution. And we could go ahead and write, just like we've done for many of our other reactions, an equilibrium constant expression, saying that K is equal to the concentration of H3O plus times the concentration of OH minus. Well, we're going to go ahead and give this equilibrium expression a very particular name, and we're going to call it KW. W here, kind of referring to the water that we have here. So it's the autoionization constant of water. Now, if you measure the equilibrium concentrations of H3O plus and OH minus for a solution at a temperature of 25 degrees Celsius, or room temperature, you're going to find that the H3O plus and the OH minus concentrations are both equal at a neutral level to 1 times 10 to the minus 7th. So that's going to imply, if we plug that into our expression here, 1 times 10 to the minus 7th times 1 times 10 to the minus 7th, that our Kw is equal to 1 times 10 to the minus 14th. And this again is at 25 degrees Celsius. So this equilibrium constant is a very, very important number. You'll find it on your reference table, knowing that Kw is 1 times 10 to the minus 14th, and this expression for how to find it here. Now, this is at a neutral pH. And notice this definition of pH is already sinking into our language here. So let's talk about where pH actually comes from. So we've noticed that acidity, or acid strength, is determined by the amount of H plus, or hydronium, H3O plus, in solution. So chemists developed a way to talk about the quantity of H3O plus that we have there, and that's using a pH scale. So pH is defined as minus the log of the hydronium ion, or H plus ion, concentration. For all our purposes, H plus and H3O plus are going to be similar. And so we can use both of those definitions here. So I've got minus log of H3O plus. Now, this equation can be used in a number of different ways. First off, this expression, minus log, can be applied to many, many different functions. We've defined pH, the power of hydrogen, to be minus log of the H3O plus, but we could define the same thing for our other ion in the ionization of water, the base ion rather than the acid. And so the POH is minus the log of our OH minus concentration in solution. The other way we could use this is we could apply this same idea of this minus log to this expression here. We could say, hey, what happens when we take the negative log of our Kw and negative log of this side over here? We have H3O plus times OH minus. Well, negative log of Kw, I know what that is at 25 degrees Celsius. The negative log of Kw, if you work it out in your calculator, is just simply equal to 14. And then I can take the negative log of this side. Now, if I have the negative log of two things multiplied together, I can express that as the negative log of just each of them added. And so I'm going to take the negative log of the H3O plus concentration plus the negative log of the OH minus concentration. And we've already defined both of those things. Negative log of H3O plus is pH. Negative log of OH minus is POH. And so I can get a new expression relating pH and OH, saying that pH plus POH is equal to 14. And so here we've set up a system. We've defined what pH is. It's just the negative log of the H3O plus concentration. And using the autoionization of water, we can see how the H plus concentration is always related to the OH minus concentration in solution. That the amount of acid and the amount of base are governed by this equation here. Let's take a look at some examples then. So what I'd like you to do here is I've got a problem for you, and I'd like you to go ahead and give it a try yourself here. Pause the video and go ahead and determine the pH, POH, and OH minus concentration using the equations we just saw for a solution with H plus equal to 5.3 times 10 to the minus 4th. Once you've done that, come on back. We'll take a look at the answers here. Okay, so taking a look at our answers, we know that our H plus concentration is 5.3 times 10 to the minus 4th. So the first thing that might be easy to solve for is our pH. To find the pH, we're going to go ahead and plug that in to our minus log of the H plus concentration. And again, remember, we can use H plus or H3O plus in either of these equations here. That's minus log of 5.3 times 10 to the minus 4th. When I do that, I go ahead and get a pH of 3.3, taking care of the mind of sig figs. Now, I have two options here. I can either find the OH minus concentration or the POH first. I find it's going to be easy to find the POH first. To find the POH, all I need to do is go ahead and solve out that POH plus pH equals 14. Since I know my pH is 3.3, I know my POH is related by that equation. So POH then is 14 minus 3.3, or I get 10.7. And finally, to find my OH minus concentration, there are two ways, and I want to show you both just to make sure that you've seen them. First off, I can find it using the definition of the POH. The POH is minus the log of my OH minus concentration. Now this is a bit harder to solve. I'm going to get 10.7 is minus the log of OH minus. And so to solve that out, I need to undo the natural logarithm. So I'm going to get that OH minus concentration is equal to 10 to the minus 10.7. And so when I do that in my calculator, I get 1.9 times 10 to the minus 11th. Now there's one more way you could do this, and that goes back to the definition of Kw. Kw is H3O plus times OH minus. And so since I know the H plus concentration, I could say that Kw is equal to H3O plus times OH minus. This is 1.1 times 10 to the minus 14th. That's going to be equal to 5.3 times 10 to the minus 4th times our OH minus concentration. And if you do that in your calculator, you should end up getting a similar number to what we saw before. Maybe a little off due to rounding or sig figs, but should be very similar there. Just lastly, I'd want to take a look at a normal pH scale. If you've probably seen pictures like this before relating different pHs, and we just want to make sure we connect the fact that if you have a large pH, you have a high amount of OH minus concentration, because the larger the pH, the more basic your solution is, because remember, it's the negative log, so it's inversely related to the amount of acid in there. So the bigger the pH, the more basic your solution is. So bases have any pH at room temperature above 7. So getting things like human blood, which is slightly pH, baking soda, milk of magnesia, ammonia, oven cleaner, sodium hydroxide, all of these things are bases, and they're going to have a higher pH than 7, our neutral pH. And remember that neutral pH, it's not a coincidence that it's equal to 7. You notice that at room temperature, just with the autoionization of water, 1 times 10 to the minus 7th was our concentration of hydronium. And so when you take the negative log of that, you end up getting 7 for both your pH and your POH. Now finally, on the other side of the scale, for low pHs, we have acids, because remember, low pH, it's inversely related with the H plus concentration, means you have a high acid concentration. So these are going to be our acids here. So things like milk, rainwater can be slightly acidic, coffee, vinegar, lemon juice, stomach acid, all of these things are going to have a low pH because they're acids.